In section 4.5, we're going to talk about linear approximations and differentials. We're going to do the linear approximations first. And here we're going to use derivatives to help us find some approximations, typically for function values that are really close by, some easy function values that we could do by hand. The idea here is usually to be able to do these without a calculator, but obviously you could use a calculator for anything. The whole point is when you have a nice, smooth, continuous function, if you were to zoom in at one particular point, zoom in really, really, really far, that function would look almost like a straight line. So I have a function we're going to look at and we're going to do an example with, and we're going to come up with its linear approximation, and then we can use that linear approximation to make some guesses for what some of the values are on that graph around a particular point without having to necessarily use a calculator, and without having to use the function itself, but rather just a linear equation. So I'm going to go over to Desmos and I'm going to show you an example of a smooth continuous function, and we're going to zoom in on this at one particular point quite a bit, and we're going to look here at 4 on the graph of y equals the square root of x, and we're going to zoom in really, really, really close. And the more and more you zoom in, you see that this just looks like a straight line. The closer and closer you zoom in at this point, and I can't get exactly on it, there you go, 4, 2, it just looks more and more like a straight line the more and more and more we zoom in. Now if you zoom out, we can tell it's a curve. But the idea with linear approximations is when you zoom in and you get really close to 4, it doesn't look so much like a curve anymore. It looks more like a straight line. So with linear approximations, you want to stay pretty close to the point that you're identifying. We're always going to identify a particular point to work with. So we're going to work with the square root graph, and we're going to work with the point 4, 2. And look at some different things that are happening around 4, 2. And we're going to see that we can get some pretty close approximations for the square root function by using just a linear equation, because really, really close to 4 on this graph, as long as we stay pretty close, it looks just like a straight line. So very close to a particular point. If you zoom in close enough, it resembles a straight line. And the slope of that line is the same as what the slope of our tangent line would be. And you remember how we find the slope for tangent lines? That is just derivative. So I'm going to write a formula here, and you've actually seen this formula before at some point in your life, but it's going to look a little different. This is technically just the point slope form for a linear equation, but we're going to throw some calculus in it. So the algebra form that we're probably all used to is y minus y1 equals m times x minus x1. So that's what we learn at some point throughout our life in an algebra class. But we're going to change this up just a little bit. Once we get a little bit more sophisticated in our algebra, we just said a second ago, we're going to always identify a specific point that we want to work with, because this only works on and around a specific point on a graph. So we're going to say at a comma, well, let me do it this way. At x equals a. Let's say that. At x equals a. So I'm going to start replacing a couple things. So this is the specific x value that we're interested in. And we like to use function notation. So the y coordinate there is f of a. So this is going to go here. So now we have y minus f of a equals m times x minus a. We also just said a second ago, the slope we get now that we're in calculus by doing the derivative. And we specifically want tangent slope at this particular point, x equals a. So the slope, tangent slope, is going to be f prime of a. So I'm going to do one more rewrite. We get y minus f of a equals f prime of a times x minus a. And if we wanted to, we could solve this for y. We usually like equations solved for the output variable, and we could do that if we add the f of a over. So this would be y equals f of a, which is just a number, plus f prime of a times x minus a. So this y value is an approximation for, this is a linear approximation for f of x near x equals a. Now, if we move too far away from x equals a, it's not going to be a good approximation. If you look back at our y equals square root x graph, as long as we stay really close to 4, a straight line is going to work. But as we move farther and farther and farther away from 4, it is not going to work. I believe the equation for this line, and I'll show you, actually, let's figure it out, and then we're going to draw it. Let's figure it out first. So we want to know what the linear approximation is at x equals 4 for f of x equals square root x. So we've got everything we need to know. This is actually a equals 4. We've got that denoted by a in our formula. So there's a couple things we need to know. We need to know f of a and f prime of a, and we can plug all that stuff in and come up with a linear approximation. Another way that this is often written is L of x for a linear approximation for our function. So f of a, or f of 4, is square root 4, which is 2. So we're going to need that. And then we also need f prime of x. That's our derivative. So remember, square root x is x to the 1/2. So we just need to do the power rule on that, which is 1/2 x to the negative 1/2, or 1 over 2 square root x. And then we'll plug our 4 into there as well, which is 1 over 2 times the square root of 4. But the square root of 4 is 2, so we really have 2 times 2 in the bottom. So f prime at 4 is 1/4. So we'll take these values, and we will plug them into that formula we just came up with, which really is just the point slope formula with some new things that we've learned plugged into it. Our linear approximation is f of a which is 2, plus f prime of a times x minus a. So 2 plus a quarter times x minus 4. Now if you want to, you can go ahead and distribute in combine like terms. This is 2 plus 1/4 x minus 1. And we could put together the 2 and the minus 1 and say that our final answer for our linear approximation is 1/4 x plus 1. And you'll see when we plot this in Desmos next to our function, sorry, plus 1. There we go. Let me make sure I fix it over here. No, it was plus 1. 1/4 x plus 1. That is our tangent line at 4. And our function and our tangent line are nearly indistinguishable in this nice little area around 4. But as we move away from 4, that the line and the function diverge. They kind of move away from each other. So the line is not going to give us a good approximation for the function the farther and farther that we get away from 4. But as long as we're staying pretty close to 4, and it looks like maybe 1 unit to the left and to the right, we can use that line to get a pretty good approximation for our function. Now, every single function is different. Some functions we can move really far away from our value, and some functions we can't move very far at all. Every single function is different. It just depends how quickly that function is changing. So we've got a linear approximation for f of x equals the square root of x at 4. And we can use this linear approximation to estimate some values on the square root x graph, because that line and the square root x function, as long as we stay pretty close to 4, they have very similar values. You can see that the blue graph and the red graph are nearly right on top of each other. So if we wanted to use our line to estimate let's say the square root of 4.1 and the square root of 2.9. So 2 examples. So 4.1 is really close to 4. 2.9 is a little bit farther away. It doesn't matter that one of them is to the right of 4 and one of them is to the left of 4. That doesn't matter at all. So this x value that we have in our linear approximation is the value under the square root, because x is the number under the square root in our function f of x equals square root x. So they're asking us to find the linear approximation at 4.1. So we're going to do 1/4 times 4.1 plus 1. And a lot of times this could be something that you could do without a calculator. But that doesn't mean you're not allowed to use a calculator. We could just potentially do this without. So 4.1 times a quarter and then plus 1 more. So a quarter of 4.1 is 1.025, I believe. And then plus 1. So 2.025 is my guess using our linear approximation for 4.1. And if we want to, we can compare that to the exact value of square root 4.1, and that one we will have to use our calculator. So if we type in our calculator and ask what the exact value for square root of 4.1 is, and let me grab my calculator. Square root of 4.1 according to the calculator is 2.02484567.3. And this is an irrational number. The result is a never-ending, never-repeating decimal. But if you round this to 3 decimal places, it's going to come out the same, 2.025. So we can find that value without a calculator. Now, a lot of people might not be comfortable doing 4.1 times a quarter in their head, but it's something that we can easily do without a calculator that has a square root button. Or it's something that we could technically write out by hand and figure out on some scratch paper, where a lot of people wouldn't know how to do the square root of 4.1 out by hand on some scratch paper. So square root of 2.9, let's try another one. So we will look at the linear approximation for 2.9. Now, this number is a little bit farther from 4. Remember, we set this entire linear approximation up around 4. So it doesn't surprise me that at 4.1, those two numbers came out really, really close. It's possible, since 2.9 is a bit farther away, our numbers are not going to come out as close as they did at 4.1. So our linear approximation said we're going to do a quarter times the x value and then add 1. So a quarter of 2.9 is 0.725. And then if we add 1, we get 1.725. So that is our linear approximation. This is a point on our tangent line. And if we want to see how close we are, we can see in the calculator what the square root of 2.9 is. And the only way to do that is with the calculator, where a quarter of 2.9, we technically could figure that out by hand. So on the calculator, the square root of 2.9, again, it's an irrational number. We've got to write out a whole bunch of decimals for this. It's 1.702,938,637. So like I said, we're not quite as close. If we round it to 3 decimals, it's 1.703. It's pretty close. We've got the tenths, the ones position correct, the tenths position correct. Our hundredths position is off. We're off by 2 hundredths. But that's because we just moved quite a bit further away from 4 than we did on the last one. So really, all these linear approximations these are just equations for the tangent line. And we set them up using point-slope form. All it was point-slope form. And then we just replaced a few things. We know we want to do it at a specific point, so we replaced the x1 with the value we wanted, and then we replaced the y1 with the functional value, so a and f of a. And then we're working with derivatives here to tell us slope. So I replaced slope with f prime of a. That's how we find tangent slope. And then I just solved it for y. We like our equation solved for the output variable. So we added the f of a over. And we said y, the output value, and this is on the line because this is the equation for a line. The output value on the line is f of a plus f prime of a times x minus a. This is going to give us a linear approximation for a function value. And as long as we stay close to that a value, which in this case was 4, we should be able to find a pretty good approximation for some different values in that function. Now, just to be crazy, I'm going to go really far away from 4 and show you how this can really fail. If I wanted to find, and I'm going to tell you this is a big fail. We don't want to do this. This is called extrapolation. When you try to use some data based on a specific point and use it to make predictions for something that's too far away. So if we tried to use this data to figure out the square root of 31, square root of 31, that is so far away from 4. I don't think this is going to give us a good approximation at all. But technically, our formula says the linear approximation at 31 is going to be 1/4 times 31 plus 1. So 1/4 of 31 is 7.75. And then we have to add 1 to it. So we get 8.75. So according to our tangent line, we think that the value for square root 31 is roughly 8.75. In the calculator, I have a feeling it's not going to be as close. So the calculator says the square root of 31 is 5.567764,363. So yeah, we are over 3 whole units away from the actual answer. And that's because we went so far away from where we said we were going to center this linear approximation. So that value of x equals 4, where we said we were going to use in our equation, that's called the center. And we only want to use our linear approximation for values right around 4. Otherwise, the approximations aren't going to be any good. And this only works, and I know I've already said it, but this only works for smooth, continuous functions. If your function is not smooth and continuous, then you will not be able to zoom in really, really close and have it look like a straight line. For example, if your function has a hole, or a jump, or an asymptote, or a sharp corner, then you will not be able to zoom in and see a straight line. So it's only for nice, smooth, continuous functions. We can use our approximations, our linear approximations, and the exact values to help us find the error in our approximation. And this is actually one of the really good applications in this section. And one of the things that we can use this for in real life is for finding error. And we are going to do actual minus approximate divided by actual times 100. This is going to give us a percent error. It's going to tell us how much we're off by as a percentage. So sometimes just subtracting them is not enough to really give us an idea if we're off by a lot or if we're off by a little. So percent error, we've got absolute values in the top because we we really don't care if we're over or if we're under. So it doesn't matter which one's bigger and which one's smaller. So we use the absolute values to throw out a negative sign. We want the actual value. In this case, we want the actual value of square root 31 minus our approximated value, and then divide that by the actual value. That's going to give you a decimal. And then if we multiply it by 100, it will change it to a percent. And that's the error in our linear approximation. It's our percent error. So for square root of 4.1, I don't think there's much error in that one. We were really, really, really close. So the actual value of square root of 4.1, and we're going to have to use a few decimals in order to get any sort of difference here. I'm going to say 2.0248. And then our approximate was 2.025. And then we're going to divide that all by the actual, and then times 100. That will change it to a percentage for us. And this will tell us how far we're off as a percentage. And it is tiny. We are off by, excuse me, as a percentage even, it's a tiny. We're off by 0.01%. We're off by 100th of a percent. So one of the examples, the practical examples that comes to mind is manufacturing. When a company produces things, especially when machines are used to manufacture any sort of object like a can or a bullet, or you might want to compare what they're actually producing to what you intended them to produce to see if the machines are malfunctioning. And you can compare what you wanted it to produce to what it actually produced, and see if there's any error in your production line. And this is a phenomenal error. Being off by just 100th of a percent is beautiful. And let's check the error on our 2.9. Now this one was a little bit bigger. This one was off a little bit more, so let's remind ourselves of those values. So our actual, and we'll just use the 3 decimals here, the actual value for square root 2.9 is 1.703. But our linear approximation came out 1.725. And we divide by the actual because we're interested in seeing how far off of the actual value of square root of 2.9 we are. And then we multiply it by 100 to change it to a percent. And those absolute values will do away with any negative because we're not concerned with whether our linear approximation was over or under the actual. So just ignore any negatives in the numerator. So this one still wasn't too bad. When you subtract and then divide and then multiply by 100, you get about 1.3%. That's still pretty good. 1.3% error. And then we're also going to do the error on our 31, which we saw square root 31, our linear approximation was way off of the actual value. So I'm expecting this error to come out really big. The actual value for square root 31 was 5.568. And then our linear approximation said it was going to be 8.75. Those two numbers are not very close together. Yeah, this is not good. We got a 57.15% error. That is bad. And if you think of an application problem in terms of manufacturing, if you were a soda company, or if you were a caviar company and you were filling your cans with your products and you accidentally overfilled your products by 50%, that would be a huge loss. So that's something that you would have to keep a very close eye on and measure regularly, and be able to adjust that quickly, or your company would be in big trouble. So there is a slight variation in this formula that uses a little bit different of a notation, and I do definitely want to show you that, because if you're going to take any more calculus after Calculus 1, you will see it again, and it uses some very specific notation that's going to pop up again later, and it's important for you to know the difference between these different notations. So I'm going to refer back to this formula that we used, and I'm going to replace some things, and we're going to talk about some different ways to write these. So I'm going to start back with this: y minus f of a equals f prime of a times x minus a. So we said that's just the point slope formula, and we plugged in a little bit of our calculus, we plugged in a little bit of kind of function algebra notation to our point slope formula. So this is just some other notation, or another version for our linear approximation. So one thing to keep in mind as we do this, in math, if you see a triangle, and not like in geometry you see a triangle with sides and angles labeled, but as a math symbol, triangle means change. And usually when you're asked to find change, you do subtraction. And there's a lot of subtraction in that formula we just saw. So we're going to be replacing some of that subtraction with our triangle symbol. And that triangle symbol has a name. It's delta. It's the Greek letter delta. So we had y minus f of a equals f prime of a times x minus a. We said this was point slope form with a little bit of calculus and function notation plugged in. Well, y is, if we further extend our function notation, y is the same as f of x. So what we have right here is just a difference in y values. This is an exact y value, and this is an approximate y value. This is the y value right at the, this is the y value right at the point that we initially plug in. It's the y value right at the initial point used to set up the linear approximation. And the y value up here, which is the y value we end up solving for, this is the y value that we're coming up as an approximation for our function. This is a y value approximation for the function at a value close by x equals a. And we're subtracting them. They're both y values, and we're subtracting them. So really, we're finding a change in the y value. So that entire left-hand side, I'm going to replace with change in y. Because all we're doing there is subtracting two y values. Anytime you see subtraction, it means change. And in math, change, we very often use the symbol delta. So that entire left-hand side, I'm going to change to delta y. And just like we did that with the y values, we're going to do the same exact thing here with the x values. The a is the initial x value that we're using to set up our linear approximation. And the x is the one that we're going to replace with the value that we're trying to calculate. So delta y equals f prime of a delta x. So the difference with this formula is it doesn't allow us to plug values, each of those points in individually. What this tells us now is just the difference in the old y value, the new y value, the old x value, the new x value. And when you're using the symbol delta, it's specifically referring to linear approximations. It means you're doing this with the help of a straight line. We are going to see one more version of this that's going to change it very slightly. So we can come up with the same answer using this formula. We're just going to go about it a little bit differently. So I want to do one of the same exact problems again so you could see that we come up with the same answer, and you can see how our work is going to change just a little bit. And I want to do the square root 2.9. So we're going to approximate the square root of 2.9 using that formula. So what we're going to think about is the change in the x values. So 2.9 is really close to a perfect square. It's really close to 4. So I want to know how far away it is. What's the difference? So that delta x is how far away is it? So 4 minus 2.9. Delta always means change. Change is subtraction. So 4 minus 2.9 is 1.1. Delta x is 1.1. That is how much my x value changed. we're still using f prime of a because we're still using the tangent slope of the function at 4. We're still basing everything around 4 here. And we said that was going to be 1/4. So according to this equation, the change in our y value should be equal to 1/4 of 1.1. So whatever 1/4 of 1.1 is, that's how much our y value is going to change. So when you first get this answer, it's not going to look right. But we're not done. This is saying that the change in the y value is 0.275. Well, change in y means whatever our y was initially, it's going to change by 0.275. So when we're comparing it to the y value at 4, the y value at 2.9 is going to be 0.275 different. So I had done the bigger, I had gone 4 minus 2.9, so I had gone bigger to smaller. So I'm going to do the same thing here, bigger to smaller. So we need to know change in y is the y value at 4, so square root 4, minus our approximation for square root 2.9 is 0.275. And I want to change those to squigglies. So this is like an unknown right now. We're trying to figure out what our approximation for the square root of 2.9 is. So I'm going to have those two guys switch spots. I'm going to add the square root 2.9 over, and I'm going to subtract the 0.275 over. So my approximation for square root of 2.9 is square root of 4 minus 0.275. It's my y value for this one minus delta y. Well, square root of 4 is 2. 2 minus 0.275 is 1.725. And is that what we got earlier? I believe it is. I just saw it right there, but let's go all the way back up. It certainly is. That is what we got earlier. So it's the same exact idea, except it calculates the change. Instead of calculating the entire new value, it calculates the change. So when we have our square root x graph, and here's 4, it's saying, I just want to move a little bit. So here's 2.9. This distance is change in x. So I need to go that way to get to my new x value. And we're trying to figure out how to get to the new y value. That is delta y. It doesn't give me the new y value. It doesn't say what this is. It just tells me how it's different than the old y value. It tells me how much it went down or up from the old y value. So it's just a comparison. It's just a difference or a change. The last thing in this section is a discussion of differentials. So far, everything that we have talked about has just been an approximation based on the tangent line. So a differential, so with differentials, we're going to make more of a distinction now between how that y value is changing and whether the change is along our tangent line or whether the change is actually along our function. So I want to show you our square root function again, but I'm going to zoom in really close. Actually, no, I'm not, because we want to see a more dramatic change. So I'm not going to zoom in close. Never mind. And I'm just going to do it here because I need to draw a whole bunch of stuff on it. So let's say that's our square root x graph. And here is 4. So when we drew our tangent line, we said that was our linear approximation. We called it L of x. So this is f of x equals square root x. And then we had L of x equals 1/4 x plus 1. That was our linear approximation for square root x. And as long as we stayed pretty close to 4, those two had very similar values. If we moved too far away from 4, then the y values weren't very similar. So I am going to work off of this other format that we talked about where we're not looking at specific x and y values, but we're just looking at the change in the x and y values. So this value here, if we follow 4, x equals 4 to the y-axis, that is f of 4, or square root of 4, which is 2. Now, if I move over to this point, which is 1, and 1, that point is on the square root graph, and the square root of 1 is 1. But if you look and see, it's a very different point on our on our tangent line with our linear approximation. We'd get something completely different. So the y value on the line is very different than the y value that we get from our graph. So we said just a second ago, when we use our linear approximation, the change in the y value is equal to f prime of a times the change in the x value. And the way that this looks on the graph is the change in our x value is the distance from 1 to 4, that's delta x. And then the change in our y value is the distance between the y value at 4 and then the y value on the line at 1, because we are using our linear approximation. So whatever this is right here, I'm going to call it L of 1. It is our linear approximation at 1. This value, or this distance right here, is delta y. So what a differential does is it wants to know how the value is actually changing on the function. So a differential is doesn't use the delta, it uses the letter D. So let me label this. And this is not using the linear approximation, this is using the actual function. But I'm going to call it the differential. So the formula for the differential looks nearly identical. It just has a couple of little notation changes. The differential says dy equals f prime of x. We can plug a specific value in there if we want to. This is just a general formula for the differential times dx. So instead of the deltas, we use d's. Now, dx and delta x are the exact same thing. I'm going to show you why on the graph. They both represent the change in the x value. And it doesn't matter whether we're using the line, the linear approximation, or whether we're using the function. The delta x is exactly the same. So I'm still interested in that distance. So whether I'm going to use my line or whether I'm going to use my function, I'm still talking about the exact same distance on the x-axis. What has changed is my distance on the y-axis. So my initial y value was up here at 2. If I use my line to estimate my new y value, I only ended up here. That's delta y. If I look at where my function really ends up, it's here. That distance between my original y value and my new y value based on the function, that is dy. dy is based on the actual function values. And we can get that with our differential. So dy and delta y are not exactly the same thing, but dx and delta x are always exactly the same thing. Now, as long as we stay really close to a, then delta y can be used as an approximation for dy. dy is approximately delta y. They are not equal, but they are approximate. And we actually write this in reverse. We say that delta y, which is what you get when you find the function value at x plus dx, plus or minus, depending on whether you're moving forwards or backwards, minus your function value, is approximately your delta y, your dy. We can get delta y, or we can use dy, which is your old function value minus your new function value. We can use that as an approximation for dy, which is our differential, which is purely based on our function in calculus, which is f prime of x dx. Now, this is kind of confusing. We're not going to do a whole lot with it now. The most important thing that I want to point out is that dx and delta x are exactly the same thing. And that's because x is the independent variable. We get to choose what we're going to do with x. So either way, whether we're using the line or the graph, that distance in the x direction is exactly the same. But what changes is the y coordinate and where we land ultimately on the second point. If we follow the line, we're going to land in a different spot than if we follow the function. If we follow the line, the difference in the old coordinate and the new coordinate is delta y. If we follow the function, The difference in the old coordinate and the new coordinate is dy. As long as we are estimating values very close to x equals a, delta y is approximately the same as dy. If we move too far away from x equals a, then delta y and dy are not the same, as we saw when we tried to do square root 31. So for right now, really the only thing we're doing with differentials is just writing out what the differential is for a specific function. And this is just a formula that's going to tell us how the y value is changing if we know how much the x value is changing. So on the graph of f of x equals 3x squared minus 5x plus 2, we're going to find the differential. So with the differential, the dy is just a set piece, the dx is just a set piece, and what we do is we throw f prime in there. So we say dy equals, and then we're going to take the derivative of our function, which is 6x minus 5 dx. What this means is small changes in x multiplied by 6x minus 5 will tell us how much the y value changed. This only works for small changes in x, though. We don't want to move too far away from the initial value that we're interested in. F of x equals, let's say, cubed root of x. We want to know what the differential is, which tells us if I slightly change my x value, how is my y value going to change? So part of this is just set. We say dy equals, and then we do the derivative. So for the derivative of cubed root of x, we have to rewrite it as x to the 1/3. And we're going to do the power rule. So 1/3 x to the negative 2/3, and then dx. So to find out how much our y coordinate changed, we multiply together 1/3 x to the negative 2/3 by the amount that our x coordinate changed. And that x coordinate, the change needs to be pretty small, otherwise it's not going to be very accurate. And we're going to look at one application problem really quickly, and that will be the end of this video. So I am looking at, let's see. Page 289 in our book, number 58. And it's a formula that has the ideal gas law. It says the pressure P, temperature T, and volume V of an ideal gas are related by PV equals nRT, where N is the number of moles of the gas and R is the universal gas constant. So P equals pressure, T equals temperature, V equals volume, N equals number of moles. And R is universal gas constant. For the purposes of this exercise, we're going to let N times R equals 1. Therefore, they're saying that we're really using the formula P equals T over V. That's the formula they want us to use. Suppose that the volume is held constant. So V is a constant. Don't think of V as being a variable. V is just some constant number. We just don't know it right now. Suppose that the volume is held constant and the temperature increases by delta T equals 0.05. So P is our output variable, T is our input variable. Temperature increases by delta T equals 0.05. What is the approximate change in the pressure? So change in pressure. Change in pressure. Does the pressure increase or decrease? So remember, change means subtraction or difference, and we very often use the delta symbol. So they tell us the change in time, and they want to know change in pressure. Well, we have a formula, and it was the second formula we went over that says delta P equals P prime of T times delta T. So what we need is our derivative times delta T. So delta P, change in pressure, is the derivative of P with respect to T. So here, T is linear. T is a linear variable, which means its derivative is just the coefficient, the 1 over V. And then delta T is 0.05. So delta P equals 0.05 over V. So the temperature increased by 0.05 of a degree. That's what this means. Pressure changed by 0.05 over V. Now V is a constant. So if you take any volume and plug it into this formula and plug it into this formula, do you think this new one is going to be bigger or smaller? And if you're not sure, you can plug in some formulas. Plug in some numbers and see. So the change in pressure is 0.05 divided by V. They want to know if that's an increase or a decrease. Well, the easiest way to tell is the fact that it came out positive. Since it's positive, it's an increase. One thing I like to think about when I think of gas and pressure and temperature is steam. This sounds really silly, but if anybody's seen the old movie Bone Collector with Morgan Freeman, I think it's Morgan Freeman. No, it's not Morgan Freeman. Never mind. It might be. Completely off topic. But they send this detective down into underground into an old under the city where they've got steam running through pipes, and the pressure builds up so great as the steam runs through that the pipes burst. So as the temperature increases, the pressure is also increasing. So, but just the fact that the number came out positive means it's increasing. If it comes out negative, that means it would be decreasing. In part B, it says, suppose the temperature is held constant and the volume increases by delta V equals 0.1. So a whole new type of problem here. This time we're going to let temperature be constant. So now we have P equals T over V still. And I'm actually going to rewrite this because this is going to be a whole new beast. Even the derivative is going to change. P equals T times V to the negative 1. This time, T is constant. And V is the variable. That's the one we're going to be doing the derivative of. Suppose the temperature is held constant and the volume increases by delta V equals 0.1. It's a positive change. That means increase. What is the approximate change in the pressure? And does the pressure increase or decrease? So delta P equals P prime of V, because now V is the input variable on the right, times delta V. So I need the derivative of this equation with respect to V. We're going to do the power rule on our V. So delta P equals negative 1 times T times V to the negative 2. So that is our P prime of V, and then times delta V, which is 0.1. And if I rewrite this just a little bit, delta P equals negative 0.1 T over V squared. So temperature is being held constant. So the temperature here is exactly the same as the temperature at the beginning. That denominator is going to be positive because anytime you square something, it always ends up as a positive. So this is our delta P. This is the first question they asked us. Then they said, is it increasing or decreasing? Well, this time, delta P has a negative in the formula, which means as the volume went up, the pressure went down. So we gave our steam more room to move, and that released some of the pressure on it. So we gave it more volume, more area, not area, but we gave it a larger space to move around in, and that relieved some of the pressure. And there is one more part. It says, suppose that the pressure is held constant and the volume increased by delta V equals 0.1. So this time pressure is held constant. So we have P equals T over V. Pressure is constant. So I'm actually going to multiply the V over. So I'm going to say VP equals T, and P is the constant here. P is the constant. And I'm actually going to say it's T equals VP because I want T to be my output variable. And then they tell us that the volume increases by delta V equals 0.1. What is the approximate change in the temperature? And does the temperature increase or decrease? So T is equal to V times P. P is a constant. If delta V is positive 0.1, what's delta T? So here is our formula. T is the output variable. V is the input variable. So delta T equals T prime of V times delta V. So delta T equals, well, the derivative of our T equation with respect to V, V is a linear variable, so its derivative is just going to be its coefficient, which is P, times delta V, which is 0.1. So delta T is P times 0.1, whatever our constant pressure was, times 0.1. So if we increase the volume by 0.1, it is going to increase our temperature by 0.1. It came out positive. So here is the result of our delta T, and then it's a positive number, so it's going to be an increase.